Hey everybody, welcome to your first edition of Stats in Pajamas. Before we get started, we should cover some basics so that as we move through the course, you'll understand some of the terminology. Now, hopefully, we can make it this intriguing. I'm not sure if we'll get there in this first video, but certainly we need to move beyond this. So what have you gotten yourself into this semester? Clearly, this is more than just that god-awful math course that's required for your major. Really, what we're talking about teaching you is how to use a toolbox, a mathematical toolbox, that allows us to understand the patterns that we see around us and to quantify the uncertainty that's inherent in all things. And really, it all comes down to how we can use this uncertainty to make informed decisions. Because in this world, nothing can ever be proven. Nothing. I mean, not even your love for somebody. Let's get all soft and fluffy about it. Not even, say, for example, gravity, the things that we accept as constants. And there's even an example of that. Here we have an example of a study where gravity has been shown to shift slightly, so that 9.86 meters per second that you all memorized in high school could actually change. So what's nice about statistics is it gives us the ability to quantify this uncertainty. And with that quantification, we can then make informed decisions, which we can use to improve our world in many ways. So our goal is to be able to quantify all this uncertainty in the data that we collect that describes the world around us, and then use that to make informed decisions. And just so you know, that isn't sort of pie in the sky, la-la talk. In addition to all the statisticians that are embedded in organizations or institutions all over the world, there are even specific organizations designed for doing nothing more than this. And I try to tell you, this is where the big bucks are. The take-home message is that after this class, hopefully you'll be inspired to take even more statistics courses, and if not, at least know that this class will give you enough knowledge and skill set to be able to put statistical analysis as one of your skills on your resume. And it should be there. This statistical toolbox can be broken down into several different branches. I think they can be organized based on their goals. Descriptive statistics do just that. They describe data sets or samples that we've collected, but they also provide the basic information that we need to conduct any other statistical analyses. And you've all seen and learned, I'm sure, these different types of metric. These metrics should all be familiar to you, but we will go over them in a little bit more detail as the class goes on, so you can understand when to use which of these metrics and what exactly it tells you about your data set, and then ultimately the larger population that you're concerned with. Inferential statistics are when you take that information, those metrics that you just quantified for a given sample or data set, and you use that to make assumptions or inferences about the larger population that that sample represents. And this is essentially what all of our t-tests and ANOVAs fall into. When you think about all those sort of basic statistical analyses, these are very simple examples of inferential tests. And these inferential tests really are the backbone of hypothesis testing. So all of the sort of scientific inquiry that tests hypotheses about different treatments or different approaches or differences between species or relationships among variables, any of these things rely on inferential analyses, which in turn relies on the descriptive statistics that generated the metrics needed for the analyses themselves. So you can see how they're all related, even though the ultimate goal is a little bit different. Estimation statistics, or modeling as it's more commonly referred to, wants to then take that information about either the relationships that we've seen or the differences that we've seen or patterns that exist, and use that information to then make predictions under different scenarios. So an example of this would be all the climatologists who look at descriptive data about climate patterns for historical data, and then they use that information to establish relationships, right, to test hypotheses about relationships between carbon dioxide and temperature or whatever other variables you're considering. And then based on those relationships, they can use that to create a model to predict the outcome, global temperature, under different scenarios, different levels of CO2, for example. So even though all of these different parts of the toolbox can be categorized, lumped into their own different sections, and you might even have classes that just cover one specific aspect of this larger statistical family, they really all do work together. So use just your latest physical as an example, right? There are tons of descriptive analyses that doctors do every time you go in there. They do your blood work, they take your temperature, they look at your blood pressure. But then this is linked to inferential tests to understand whether or not you're abnormal compared to the larger population. For example, your blood work. Do you fall into a category of people that have heart disease based on your LDL levels, or do you not? That's where those thresholds come from. But then take it one step forward, and you can see that there are even people that would use this information to model your actual likelihood of death. And that's what actuarial science is all about, right? They try to predict, based on your health and your lifestyle characteristics, how long you will live. Pretty morbid, but again, another way that people make a lot of money off of statistics. So hopefully now you have a better idea of what exactly statistics is all about, and we're going to try to touch on each of those families as branches of statistics in this course. But before we really get into that, there are some key terms that we should review so that as we're talking about different concepts, you're not lost right from the get-go. So let's get into the really exciting part of just knowing our vocabulary. So we'll start with just some basic terms that we use to describe our data, like the measurements that are actually taken. And at the largest level, we think of the population. And the population is the complete set of all possible observations. If you were doing a study on humans, the population would be every single human being on planet Earth. If you were doing a study on Americans, your population would be every single naturalized citizen. And so the population can vary depending upon your hypothesis or what it is you're trying to test or ultimately describe, but it includes every possible unit of observation. Now, what we usually do, because it's impossible to measure a complete population just in terms of times and resources, we usually measure a sample of that population. So essentially a sample is a subset of all those possible observations, and we try to do that such that it is representative of that larger population. And typically that's done by taking a random sample. When we say something is random, what it means is that any one of those observations has an equal chance of being selected and included in our study, right? So we're trying to draw those observations from the larger population so that it truly is representative of the full population. But the catch that we have to be aware of is even after you've drawn a random sample, because it is random, it doesn't guarantee that it's representative of your sample. So statisticians will often go back and make sure that the observations they've selected by using descriptive statistics do match what they would expect to see in the larger population, right? That we're representing the full range of characteristics we would expect. Okay, and then at the smaller level, we're getting down to individual observations. So this is what we're actually taking a measurement on and using as, think about your spreadsheet, using as a row in our table. Right? Each row in a table represents one measurement, one unit of observation. But this also can be very tricky, and that's because your observations for most statistical analyses need to also be independent. So this is another term that we'll have to become familiar with. And to explain that, I think it might actually be easier if we use an example. So here we are in a forest over in Underhill, not far from us. And we might go into a plot, right? So let's imagine we have a fixed radius plot. I'll draw a plot right here. Here's one plot, and we'll put another plot over here. And imagine these plots are randomly selected, right? So they're sort of put out here in space in a random manner. And I might go in and actually take growth measurements on each tree. So in this case, what I'm actually measuring is the growth of that tree and that tree, and maybe even these trees are randomly selected within each plot, right? So it's tricky because I am actually taking measurements on individual trees. And when I walk out of this forest, I'm going to have a unit of growth for each of those individual trees. But because these individual trees are not independent of each other, so independence means that your choice of any one measurement is in no way connected to another measurement. But in this case, I knew that all of my trees had to fall within this plot, and therefore they're not truly independent, because when I selected this tree, I knew I had to select another tree within this fixed radius. That's not independent. So instead, what these trees become are replicates in the larger observation, which is the plot. So in this example, my unit of observation for my statistical analysis, where I know that each observation is independent of each other observation, has to be the plot. And then nested within that, I have these replicates of trees. Right? So it can be a little bit tricky. An observation typically is that one unit upon which you make a measurement and record data. However, the caveat is that they have to be independent of each other, right, for most analyses. And in this case, the selection of these trees, because they are bound geographically, is not independent. So instead, what I would end up having is I would have all of these replicates of sort of randomly selected trees within each of my plots, right? And these randomly selected trees are actually replicates within this larger unit of observation, which is the plot. And we'll be practicing some more with this, but this is just one of those sort of caveats to keep in mind as we work through other examples. So just to reiterate, we know that our observations are independent if the selection of any one of those doesn't influence the selection of any other observation, right? So typically, again, our observations have to be independent, and if they're not independent, then it means that we have replicates within a larger unit of observation, right? And this is very common in natural resources because it's nice to represent the variability that we might expect to see within our unit of observation. And there are now complicated ways, but there are also easier ways to deal with this, right? So one simple way to work with replicates is just to average them and use the average metric as your unit of observation, right, your actual data value. And then there are more complicated ways, nested analyses, that if we have time we might get into, that allow us to actually also evaluate how much variability there is within those replicates. So now we understand ways to describe what we're taking measurements on, but how do we describe the actual measurements themselves? Well, these are referred to as variables. And it's some quantity, some metric that we are either counting or measuring or observing. And there are different ways to describe our variables. We can have quantitative variables. These are ones that actually can have a value, a numerical value associated with them. And they can even be broken down farther into continuous variables. In other words, that number, that numerical value, could be anything. It could include multiple decimal places. It could be any value across a larger range. And then in contrast, we can have discrete variables. These are really just whole integers. So maybe it could be a 1 or a 2 or a 3. Think of count data, frequency data, as a discrete variable. And we'll be primarily dealing with those quantitative variables, but there are also entire statistics courses devoted just to qualitative data. And when we're talking about qualitative data, we're usually just assigning one of our observations to a different class, right? So it could be a nominal class if there's no order implied. So an example of that might be Democrat, Independent, or Republican, right? We're not saying anyone is better or more than another. They're just different categories. But then you could have ordinal variables, and these are really common in Likert scales. So if you've ever taken a survey and they say, report how you feel about X, Y, or Z, you agree. If you agree completely, then score it as a 5. If you disagree completely, score it as a 1. And if it's somewhere in the middle, score it as a 3. Those are ordinal classes. Again, we're still looking at a class variable, but there is an implied order for interpretation to that. And then we can also get into interval or ratio variables. And these are really interesting in that they often will take a continuous metric and then convert it to an interval so that they can analyze it in a more qualitative format rather than a quantitative format. So these might seem like little nitpicky things to try to differentiate between, but what statistical analysis you use is first of all dependent upon the nature of the variables you're testing. And so knowing what type of variable you have is essential to conducting the correct test. In addition to describing the nature of our variables, we can also describe the use of our variables, how we're going to actually use that data. And we typically in most analyses have an independent and a dependent variable. The independent variable is usually I think of this as a predictor variable. What do you think is causing the differences that you see or driving the relationship? So for modeling, particularly regression, we're going to see this terminology come up. Our independent variables are the factors that we're using to create an equation that can then predict the output or the response, and that would be our dependent variable. So the way to think about that is that our dependent variable is, in fact, dependent upon the settings of the independent variables. But it gets even better, because we can take those same exact variables intended for the same exact use and describe them in other ways as well. So typically you will see those independent variables, the ones that are being used to model some response, referred to as either factors or treatments or terms or levels. If it's just an equation, you'll see them written as x, usually x sub 1 or x sub 2. So all of these different terms all are referring to the same thing, those independent variables that are being used to model some output. The dependent variable is a little bit more simple. It can be referred to as the response variable, the output variable, or in an equation just as y, the letter y. So while I don't expect you to be able to regurgitate back some definition of each of these terms, I do hope that this is going to start to sort of permeate your subconscious, so that as we're having these discussions in this class, you'll not be too confused about what we're talking about. Are we talking about an observation, about a population? Are we talking about a dependent variable or an independent variable? And we'll get there eventually. So I don't expect anyone to be dreaming in statistics quite yet, but hopefully this is a good start. So that'll be it for this edition of Stats in Pajamas. See you next time.